Hello, this is Dr. Jake Abbott. In this video, we're going to review some of the fundamental concepts of linear algebra that you should have seen in a linear algebra course, but I just want to make sure everyone is fresh on these concepts that we're going to be talking about. So, let's begin with some really basic concepts. When we're talking about linear algebra, what we're really talking about is sort of how do you multiply matrices and vectors and matrices together, and the sort of types of spaces that you can describe using these kind of vectors and matrices. So let's begin with a really basic review. So if I have some matrix A times some vector x, let's say A is an n by m matrix, and this vector is an m by 1 thing, and you know the two things that multiply together always have to be the same, so an m and an m here in this case. Now this is something that people should be very familiar with. So I'm going to have this A matrix that's going to have a bunch of little elements like this. I'm pretending there's 3 columns, and then I have a vector of things. And if there are 3 columns, then there's got to be 3 rows in this thing. And the way that I come up with entries of the resulting n by 1 thing is, for this first entry, I'm going to multiply the first row times this column, and that's going to go here. And then for the second entry, I'm going to multiply this row by this same column, and that's going to go here. And we continue with this sort of operation. Something that's pretty straightforward. To actually do the mechanics of this multiplication is pretty easy. What may not be as obvious to everyone is that if you think of this matrix written like a set of rows, so I have row 1, and I'll call that A1, and I have this row 2 like this, all the way down to row n in this case, because I said A is an n by m thing, which means n rows and m columns. And then I multiply this by this vector x, and let's not break x up any further. Then the resulting vector I get, I can think of this as A1 times x in that space, A2 times x in that space, all the way down to AN times x. And so does this make sense to us? So each of these elements, if I have n of these rows, each row itself is a 1 by m thing. And so what am I doing here? I'm really doing a 1 by m thing times an m by 1 thing, which gives me a 1 by 1 thing. So each of these little things are scalars. So this corresponds to the scalar that appeared there. But I can think of it without actually breaking m down. I can think of this matrix multiplied by a vector as being the rows of the matrix multiplied by the vector independently in this entry. And that can be something that's useful for us in the future. So sort of the next thing we might want to look at is a matrix A times a matrix B. And again, let's say this is an n by m thing, and let's say this matrix B in general is an m by p thing. And I say in general because to do a matrix multiplication, the two inner things, this m and this m, have to be the same. So I can't even think about multiplying matrices where that isn't the case. So this is sort of the general case of all possible 2 matrices that you could legitimately multiply together, an n by m and an m by p. And so when I'm done, I'm going to get some third matrix that's an n by p thing. And if you break up this matrix B, you think about this matrix B is really just a bunch of columns. So there's column 1, and then there's column 2. And how many columns are there in this? If there's m by p, there's p columns. So I go over here to finally to column p. When you think about doing matrix multiplication like this and looking at the way we multiplied A by some vector x, then when you look at a matrix like this, you realize this is really just doing each of these columns B. This is an m by 1 thing, and this is an m by 1 thing. So each of these columns of B look just like that vector x in the previous slide. So when we can do this, we don't even have to break up this A if we want. We can think of this as A times B1 in that column, and then A times B2, all the way to A times BP. This is this matrix C. And so each of these things, I mean, this is an n by m thing times an m by 1 thing. So this is an n by 1 vector, an n by 1 vector. So this is another way you can think about doing matrix multiplication. And so it's really thinking about this right matrix as really just a set of vectors where each column is a vector, and then using our intuition about how we multiply matrices and vectors. This is a trick where we don't actually have to break up A. We don't have to know anything about A to do this kind of multiplication. So I think these first two cases of A times X and A times B are things that a lot of people have pretty good intuition for. I think looking at like a left kind of multiplication is something that people have a little less intuition for. So I can also take this matrix AB, and I can think of breaking up my A matrix in terms of rows. So I can have row 1. How many rows are there? It's an n by m, so there's n rows. So I have row 2 all the way down to row n, and I can multiply that by some matrix B, and each of these things now is a 1 by m thing, a 1 by m thing, and this B is an m by p thing. So it turns out I can actually think about this as loading up each of these individual rows as A1B, A2B, all the way down to ANB. I think this is something that people have less intuition for. And this is also equal to this same matrix C, but now each of these rows here is a 1 by m times an m by p, so that means each of these things is a 1 by p row vector, essentially. 1 by p, 1 by p. And there's n of them, so the resulting thing is n by p. So this is another way that we can multiply these matrices together. And then a third way we can multiply these matrices together is we can say, well, this matrix AB is really, I'm just going to break this up into its columns, A1, A2, all the way to column AM, and I can break this B matrix up into its rows, so B1, B2, and how many rows does this have? It has M rows, all the way down to BM. And then I can actually think of this as all of these individual components added together. So A1, B1, plus A2, B2, plus all the way to AM, BM. But what are the dimensions of these things here? What is A1? A1 is an n by 1 vector. What is B1? B1 is a 1 by p row vector. So this thing here is an n by 1 times a 1 by p. So this is an n by p matrix. I'm taking a column vector times a row vector, and I'm getting an n by p matrix. And this thing here is an n by p matrix. And this thing here is an n by p matrix, which makes sense. They have to be the same dimension if I'm adding them together. So I'm taking a bunch of n by p matrices, adding them together to ultimately form this C matrix, which is an n by p matrix. So these are three completely valid and different ways to think about how you might multiply an A matrix, an arbitrary A matrix, and B matrix together. They're all valid, and they all may be powerful in one time or another. So that's some basic sort of matrix and vector mechanics that we've just looked at. So let's start thinking about, we want to think about basis vectors, and we really want to think about the kind of spaces that we're describing with vectors. So we're going to consider, in general, n-dimensional real linear spaces. And we describe this, we use this script r to the n, meaning an n vector of real numbers. So we're talking about things that look like this. We're going to consider some x, which is a big vector, x1, x2, all the way to xn. So there are n of these numbers, and each of these individual things is just a scalar real number. So when we talk about n-dimensional spaces, this is what we mean. And so a vector is sort of a, you can sort of think of it as kind of the base element in that space, but it takes n real numbers. And we have a lot of intuition for two-dimensional spaces, so R2, and three-dimensional spaces, R3, but the mathematics is going to apply to n-dimensional spaces. And in state space controls, our state vector that we're going to be considering could be many states. It could be 7 or 8 or something. And so we want to think of the math more generally, and we're going to always sort of reference back to two-dimensional and three-dimensional spaces that we have a lot of good physical intuition for, but do the math more generally for n-dimensional spaces. So we need to talk about vectors in this space, Rn, and we want to talk about linear dependence of those vectors. So let's talk about what it means to be linearly independent. So we say a set of vectors in this space, Rn, is linearly independent if, I should say if for some alpha 1 times x1 plus alpha 2 times x2 all the way, I'm going to add that up to alpha m times xm equals 0. So this is just the first half of this statement, but let's stop for a minute and look at what we're talking about here. So we have m vectors here. We're looking at this set Rn, so each of these vectors is an n-dimensional vector. So m and m are not the same number necessarily. So we're talking about vectors, so this is an n by 1 vector, x1, x2 is an n by 1 vector, xm is an n by 1 vector, and there are m of these vectors. And so I have m of these vectors, and that m could be 1, it could be 3, like I've drawn it here, but I have m of these vectors, and each one of these vectors I'm multiplying by a scalar, just some constant, and then I'm adding the resulting vectors together. So let me continue with this statement. A set of vectors in Rn is linearly independent if for this equation, so some linear combination of these m vectors, it equals 0. Okay, I've added them together and I've gotten a big 0 vector. So this is an n by 1 0 vector. The only set of real numbers that satisfies the above equation is alpha 1 equals alpha 2 equals alpha m equals 0. So what I've basically said is I have a set of these vectors and I want to find combinations of alphas that I can multiply by my vectors by and add them up, and I'll get a 0 vector. And if the only alphas I can find are 0, then these are linearly independent. These m vectors are linearly independent. I mean, think of what that's saying. I'm saying I'm multiplying them all by 0. So, of course, if I multiply something by 0, it's going to equal 0. No matter what x1 is, if I multiply it by 0, I get 0. So to say that if I have a bunch of vectors and I multiply them by 0 and then add them up, I get 0, that's a completely trivial statement. So when you say that the only set of real numbers that satisfies this is a bunch of zeros, every single alpha equal to 0, then what you're really saying is there's no way I can add up some linear combination of these n vectors and get 0. Because of course if I multiply them all by zeros, I'm going to get 0. So there's no other way to do it. And so I'm saying these are linearly independent of each other. If this isn't true, and there's some non-zero set of alphas that will let me multiply these together and get 0, then they are linearly dependent. So this is the definition of linear independence. And if they were linearly independent, then I could actually solve for x1 as some linear combination of other vectors. Or I shouldn't say that in general, but I could solve for one of the x's in terms of some linear combination of the other x's. So sort of based on my little misspeak there, let's think about this more precisely. So let's say they were linearly independent. That means there's at least one, so at least one alpha not equal to 0 would satisfy that equation above. So let's say it's alpha 1 not equal to 0 would have satisfied that equation. Okay, so if that were the case, if it were alpha 1 that could be not equal to 0, then we can solve for x1 as some linear combination of the other ones. And it's really easy to go back to the original equation and see what that would be. It would be that x1 is just equal to minus 1 over alpha 1 times all of the other ones added together. So alpha 2 x2 plus plus alpha m xm. You just go back to the original equation where you have all of the alpha 1 x1 through alpha m xm equal to 0. You bring the alpha 1 x1 over to the other side and you divide by negative alpha 1, and that's your solution for x1. But it hinges on this alpha 1 not being 0. If it were 0, you couldn't divide by it like this. And knowing that it's not 0, you can. So basically, we would have a case where you would say that x1 is linearly dependent on x2 through xm, meaning that you can write it as some linear combination of those, where the multipliers on x2 is basically minus alpha 2 over alpha 1, and the multiplier on xm is minus alpha m over alpha 1. So you can think of it as a linear combination like that. So x1 is a linear combination of the other vectors in the set. Now, a set of linearly independent vectors in Rn is called a basis in Rn. If every vector in Rn can be expressed as a unique linear combination of the set. So we're talking about basis sets, and let me restate that. A set of linearly independent vectors, so we're already assuming that they're linearly independent. A set of linearly independent vectors in Rn is called a basis for Rn if every single vector in Rn can be expressed as a unique linear combination of the set. So, in Rn, any set of n linearly independent vectors is a valid basis set. I'm going to write that out. So, in Rn, any set of n linearly independent vectors is a valid basis set. We are saying that if you want to describe any vector x that is an n by 1 thing, right? x1 ... to xn. If you want to describe any vector x, if you have n linearly independent vectors that are in Rn, there's some way that you can make a linear combination of those to make this vector x that you want. Okay? So let this set here, q1, q2 through qn. So I'm imagining a set of n vectors, which I'm calling q1 through qn. I just have these n vectors. Okay, let's let that be such a set. So these are n linearly independent vectors. So I can form any x I can imagine I can form it by some linear combination of these. So some alpha 1 times q1 plus some alpha 2 times q2 plus some alpha n times qn. Okay, and I can come up with any x I want in Rn, and there's some set of alphas that I will be able to find. This is sort of the definition of what it means to be a basis set. So we're saying that these vectors q, these q vectors, form a basis for Rn. It's not a unique basis, but it is a basis. So any set of n linearly independent vectors will work. Okay? If we define a big Q matrix, so define this matrix Q, and the way we build this matrix Q is its columns are these vectors. Okay? So up here we were just thinking of it as a set. So I just hand you a handful of vectors, but they're not ordered in any sort of way. I can just sort of tell them to you. But now we're very formally structuring a matrix Q where its columns are these vectors. Okay? So I have these Q vectors, and there's n of them, and each one individually is an n by 1 thing on itself. So I have an n by 1 thing, an n by 1 thing, and there's n of them. So this Q matrix is an n by n matrix for this space Rn. So I structure my basis set in this matrix, and then I can think of any vector, this vector x, I can always think of it as just some linear combination of the columns of this matrix. So I can write it like this. I can say it's this Q matrix, which is an n by n thing. This is an n by 1 thing. And I can think of this big Q matrix being just some set of scalars, alpha 1, the same from up above, alpha 2 down to alpha n. So this is a big n by 1 vector of the linear combinations of the columns. And when you do the vector matrix multiplication, you'll see that this equation works out to just the exact same equation for x up above. And I can call this vector here, let's say I call it x tilde, such that this is equal to q times x tilde. So basically any vector x is equal to a Q matrix, which defines the basis set of the space, times this vector x tilde, which we call the representation of the vector x with respect to this basis set. So this is the representation of x with respect to the basis set Q. So it's basically just a weighting function. If it's possible for me to build x by some linear combination of the columns of Q, then how much weight should I put on each column, basically? What should these alphas be? And so you can think of x tilde as being the set of weighting functions of the basis vectors. So we call that the representation of x with respect to this basis set Q. But the cool thing about this is, these vectors Q, there's lots of different possible combinations that would work. All they have to be is n linearly independent vectors, and that's enough to form a basis set. So we could come up with a kind of crazy basis set that doesn't have a lot of physical intuition, and then we could describe our vector x with respect to that basis set, and it would be some sort of kind of strange combination. So I'll do an example in a little while to sort of explain how that could happen. So the most common and simplest basis set for Rn is an orthonormal basis set. Okay, so orthonormal. And orthonormal means orthogonal and normal. That's where this word orthonormal comes from, orthogonal and normal. So the question is, what does orthogonal mean? Orthogonal. What orthogonal means is that if I have two vectors, if I take their dot product, I'll get 0. Basically meaning that these two vectors are not pointed in each other's direction at all. There's no component of these two vectors that will line up with each other. So if I have some vector I A, and I'm going to explain why I'm using I in just a second, and I take the dot product of that thing with this other vector, IB, then, and I'm going to show you whether you kind of remember this or not, the dot product of two vectors is the same as if I take this vector IA and I transpose it and then multiply it by IB. So these are the exact same statement. So if I take these two vectors, if they are truly orthogonal with each other, then this is going to equal 0, meaning when I take the dot product of these two vectors, there is no component in the same direction, so I get a 0. And this is true for all A not equal to B. So basically, it doesn't work if you multiply the vector with itself, but if you multiply with any other vector in this set, and I get 0, if this is always true, then this means these vectors are orthogonal. And then, what does normal mean? So normal really means what we call unit vectors, meaning length 1 vectors. So what does a unit vector mean? It means that it has a vector IA has a 2 norm, and I'll explain what this means in just a second, but it basically means length, okay? So it has a 2 norm equal to 1. So these are unit vectors, and this is true for all A. So every vector in our basis set, if it has length 1, meaning a 2 norm of 1, then these are normal vectors. And so if we say we have an orthonormal basis set, it means that we can take all of our vectors in our basis set, they're all length 1, and if we take any two of those vectors and we look at the dot product, we'll get 0. If that's true, if we meet both of these conditions, then we have an orthonormal basis set. And the most common orthonormal basis set that we use is this set that looks like this. You'll be very familiar with this. There's the vector 1, 0, 0, ba, 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 and then I2 will be this vector 0, 1, 0, 0, dot, 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 all the way to this vector, the nth vector, which I have my 1 all the way in the nth spot. So let's see, such that this x vector, which is going to equal x1, x2, all the way down to xn, is going to equal just x1, which is a scalar, times I1, plus x2 times I2, all the way to xn times In. And we can also, interestingly enough, think of this as equal to a big identity matrix times this x1 through xn. So this identity matrix is an n by n identity matrix. And we can also think of this as the identity matrix times this x tilde. And so in this case, if we use this very special orthonormal basis set, then there's no difference between our vector x and our representation of x. So basically, it's such a simple basis set that when we say let's describe a vector with respect to that basis set, the representation of the vector is the vector itself. There's sort of no weird mapping we have to do. The basis set is so intuitive. It breaks up our space into these directions in such an intuitive way that there's no like kind of further thought that needs to happen. But this is one orthonormal basis set, and this is sort of the standard orthonormal basis set that you'll see over and over. But there are other orthonormal basis sets. Just because, I mean, yes, this is a length 1 vector, and this is a length 1 vector, and these two are orthogonal to each other, and these are orthogonal to each other. But I could think of other length 1 vectors that don't have just a 1 and a bunch of zeros, and it could still be a length 1 vector. And then I could write another length 1 vector that's not just a 1 and a bunch of zeros, and I could have them still be orthogonal to each other. So don't think that this is the only orthonormal basis set. It's just a standard orthonormal basis set. So we briefly introduced the notion of vector norms. Let's talk about that a little more specifically. Okay, the norm of a vector x, and we use norm, we use this double bar to talk about the norm. It's a generalization of length, okay? And it's okay to think of length when you're kind of grounding this in your mind, but you have to also let yourself separate it from actual physical length, okay? What makes a norm? What are the definitions of what makes a norm? And there are 3 rules that it has to meet, okay? It's a real valued function. And what does that mean? These are sort of mathematical terms. A real valued function. It's a function. A norm is a function because it has an input and an output. The input is the vector x. So I give you a vector x, and then you give me the norm. So it's a function in that way. And real valued means the thing you give me is a real number. So a scalar real number. So I give you an x, you pump it through this black box, which we're going to call a norm, and you spit out a real number, and that is the norm of the vector. So that's what a real valued function means. And you could make up your own vector norms if they met these following 3 criterion. So the first criterion is that a norm has to be greater than or equal to 0 always. It's a scalar number that's a positive number for all vectors. And the norm of x equals 0 if and only if the vector itself is 0. So basically what that means is when I give you the norm, you have to give me a scalar number describing sort of the length of this vector, but length is sort of a wishy-washy term here. So it can be any real valued function, but the only way it can spit out a 0 to me is if the vector itself is a 0. So you want something that can distinguish between a 0 vector and a non-zero vector. So here's the first rule. The second rule of a norm function is that the norm of some scalar times a vector has got to be equal to the absolute value of the scalar times the norm of the vector itself for any real alpha. So this is kind of a simple function. If I multiply a vector by some scalar, then I get the norm of the vector back times the magnitude of the scalar I multiplied it by. And the third rule is that if I take the norm of 2 vectors added together, it'll always be less than or equal to the sum of the original norms. For every x1 and x2. So if you meet these 3 things, if all of these things are true, then you've just created a valid norm of a vector. So the norm we're most familiar with is the 2 norm, which corresponds to vector length. I meant to have this little 2 on the outside. So the 2 norm, and it's defined like this. You basically take my vector, you transpose it with itself, or basically dot product with itself. That is going to give you a scalar, and then you take the square root of that thing. So more formally, you can write this as the summation from I equals 1 to n of the absolute value of each of the individual entries in the vector squared, and then take the square root of that thing. This is the 2 norm, and this corresponds to, we call it the 2 norm, and it corresponds to Euclidean length. So this is the length of vectors that we're often familiar with. So if I have some space like this, and I mark out space and say I want to find out how long this vector is, you say, well, if I know the component in this direction and I know the component in this direction, you basically are just doing a triangle, and it's this sort of standard Pythagorean theorem that c squared equals a squared plus b squared. So I mean this formula applies really directly right here, right? C equals the square root of a squared plus b squared. It just goes right into this formula. But there are other valid norms that aren't directly corresponding to length. We use the 2 norm more than any other norm because it does correspond with length, and in this class we'll rely almost exclusively on the 2 norm. But there's also the 1 norm, which you can write out like this, and it has a pretty simple formula. You take the sum of, from I equals 1 to n, of all of the entries. So basically, rather than taking the square root of the thing after and doing this kind of RMS type thing, you just add up the size of each of the elements together, and that's the one norm. There's also the infinity norm, which equals the max over all I of xi. So basically, it just says, just give me the biggest entry in the vector. If my vector is 7, 1, 1, then just give me the 7. Just tell me what's the biggest thing of all the entries. Where the one norm adds them all up, right? So you can think of examples where you'd say, okay, what is the one norm? Let's look at this vector here. X equals the one I just described, 7, 1, 1, right? The one norm is equal to 7 plus 1 plus 1, which equals 9. The infinity norm is equal to just the maximum entry, so it's equal to 7. The 2 norm, which is the length of the vector as we're used to thinking about it, is equal to the square root of 7 squared plus 1 squared plus 1 squared. And so what's that? 49 plus 50 plus 51, so square root of 51. So these are completely valid norms. We're going to use the 2 norm more than any others, but they're completely valid norms. So I wanted to briefly kind of go back to this idea of orthonormal basis sets that aren't the normal standard basis sets that you're used to thinking about, and not even thinking about orthonormal, but thinking about just basis sets in general. So let's look at a two-dimensional space. So we're going to look at R2. So here's one component and here's the other component, and let's pretend our basis set was this vector here and this vector here. So our basis set in this case is Q1 is equal to the vector 1, 0, Q2 is equal to the vector 0, 1. Right? So here's Q1 and here's Q2. So it's very easy in this case. If I have some arbitrary vector in this direction, it's very easy. Let's say this vector x here is equal to the vector 3, 5. It's very easy. Okay. X is nothing more than 3 times the vector 1, 0 plus 5 the vector 0, 1. This is very intuitive. And we have a ton of intuition from other classes about looking at vectors like this. The thing that might not be so intuitive is let's look at the exact same vector. Okay. So the vector here, x equals 3, 5. So we're going to look at the exact same vector, but let's look at a different basis set. Let's say our basis set instead was this vector Q1. Q1 is equal, let's have it be the same, 1, 0. And this vector here, Q2. So Q2 is equal to the vector, let's say it's the vector 1, 1. Okay, our original basis set, we had an orthonormal set. If we have this vector's length 1, we have this vector's length 1. If we take the dot product of them together, then we'll get 0, so they're orthogonal to each other, and you can see that orthogonality just with your eyes. So if I have this set, now my Q1 is the same vector, so it's still length 1, but my Q2 is no longer length 1. It's longer than length 1. And from Pythagorean theorem, we sort of know this is like a 1, 1 square root of 2 triangle. So the length of Q2 is square root of 2. It's not 1. But it still is possible for me to express this vector x as some linear combination of Q1 and Q2. And it's sort of easy to imagine how that would happen. So I can sort of do it in a very informal way here, because the only way I can get this 5 in the 3, 5 is from Q2. So I know I need 5 times Q2 And if I were to do that, what would that give me here? So I'm trying to construct this vector 3, 5. If I took this vector 5 times q2, I would get 5, 5. So you can sort of imagine what you would need, what constant you would need in front of q1. I need to get rid of 2 up here. So, I mean, to make this 3, 5, you know what I need here. I need this to be 0 and minus 2. So if I multiply q1 by minus 2, I'll get exactly what I need. So there's some combination of q1 and q2 that give me x, and I could do that with any x. I could find any different x vector and make it as some combination of this q1 and q2. So this is a case where q1 and q2 are not an orthonormal basis set, but they are a basis set, a completely valid basis set. And then these numbers, 5 and minus 2, become the representation of x with respect to this basis set. So it's a pretty straightforward concept.